Yes, now we want to focus on another characteristic for a sample which serves a different function than merely determining the mean of a data set. To illustrate this, let's consider the following situation. Imagine we have two groups, Group A and Group B, of students taking an exam, 2001, on the left side. Here, you can see the score distribution of Group A and Group B. And what you see is that when we look at the average or the mean of the two groups, they are very close to each other, both around 90. This means that the mean and, when looking at it, the median are relatively similar for both samples. However, if we take a closer look at the sample, I have plotted it here. We can see Group A, where the mean is marked. We can observe that Group A is relatively close to this mean, meaning almost all the data points are around the center of this mean. And Group B looks as follows. Here we see that while there is a value that is very close to these, 90 points, many other values deviate relatively far. What happens, however, is that individual values balance each other out. There is a high deviation in both the negative and positive directions, and as a result, the overall center or the mean is not affected. What we want now is to identify a characteristic that can distinguish these two groups, which really indicates that Group A is somewhat less spread out than Group B, which is more widely spread. And we can do this with the so-called variance or standard deviation. More specifically, sample variance and sample standard deviation. And we will take a look at that in the following. So we have again a sample x to xn, which has a size of n, and it does not necessarily have to be ordered explicitly. So we find ourselves again in a situation where it does not have to be the case, as it is with the median and the quantile. And now we want to define the so-called sample variance, which is often used in statistics. And what we are going to look at for this is, we will build it step by step here. So we want to examine the distances of the individual points from the mean. Let's just take a quick look at this again. We simply want to determine the individual distances from this value here, and more or less find the center or the mean. So the idea is that we want something like this arithmetic mean of these deviations from the mean, and we want to do this in such a way that positive and negative values do not cancel each other out. So this distance here should not balance out with this one, as happens with the mean. And we do this as follows. First, we describe the sample variance with S. And now, as I already mentioned, we look at the distances of the points from the mean. We want to do this in such a way that they do not cancel each other out, meaning that the deviation to the left and the deviation to the right balance each other. And we could either do it by taking the amounts of, so to speak, psi x, or alternatively, we take the square. And indeed, the square has prevailed, meaning that we are considering the sum of all squared distances from the mean. And now we would theoretically determine the mean, which would be 1 divided by n. But for technical reasons, which we unfortunately cannot go into in detail in this lecture, it is done as 1 divided by n minus 1. So a little less than 1 divided by n. So as I said, we would actually expect to take 1 over n, really taking the average of all distances, but for technical reasons, we do not do that. Instead, we just have to remember to take 1 over n and This is now somewhat similar to the root mean square distance from the mean, and thus serves as a measure for it. If this is generally large, it means that the points are indeed on average very far from the mean. And because it is the mean, it must naturally be removed in some way from both the right and the left. And now we want to introduce another term, namely the standard deviation. And there is the idea, because we are taking squares here, that we want to normalize it again. And so, what is that? How can I reverse the squaring, so to speak? I take the square root of the whole thing, and then I no longer write s, but s, and I call that the sample standard deviation, or the standard deviation of the sample. And here, it is important that the square root essentially applies to the entire term, including the 1 over n. And if we take a look here, we have both groups. We have the means. And now we can also examine how large the sample standard deviation is. That means this length here, it is common to draw it like this. This is our S, the sample standard deviation of the blue. That is group A, and this distance here is the sample standard deviation of group B. And there we see clearly that the sample standard deviation of group B is significantly larger because it spreads further around the mean. And exactly, they will practice this again shortly with an example. But essentially, the idea is that we now also have a metric for the dispersion of samples. And that was it for the first week. And I hope you were able to take something away from it, and we will see each other again in the second week. Until then.